The first derivative is a function. So far, we've talked about the derivative in the following way. We've said at a particular point A, we have found the limit as h goes to 0 of f of a plus h minus f of a over h. And what this gives us is the slope of the tangent line at x equals a. And of course, this ratio here actually comes from taking a secant line and then taking the limit as the 2 points on the secant line get closer and closer. And of course, the limit of the secant line is a tangent line. Now we're going to reconceptualize this ever so slightly. What we're going to do is, instead of putting an a there, we're just going to leave it as an x. So f of x plus h minus f of x over h. And then what we're going to get is a derivative function. That is to say, at any point x that we plug in, we'll get the slope of the tangent line. So just as the original function has an input and an output, this function has an input, which is the x, and its output equals the slope of the tangent of f of x. So if you imagine, say, having a nice smooth function, say a polynomial function, which is smooth, continuous, differentiable for all real numbers, function number one, the polynomial, has an input and an output for all real numbers. Now if we take the derivative, that will give us another function, a second function that will also have a domain of all real numbers, and at any real number, its output will be the slope of function number one, the slope of the original polynomial. So there are a couple ways that we can write this when we're writing the derivative. We can either write it in this notation, which I have been using, f prime of x. We can also write it in this very different notation, df of x over dx. Okay, that is supposed to be evocative of the deltas, delta f of x over delta x, which is kind of what we have in the ratio up here. This notation, f prime of x, was first used by Mr. Newton, who was the original inventor of calculus. This notation here was used by Mr. Leibniz, who invented calculus independently of Newton. And as we'll see, the Leibniz notation, although it does look like it takes a little more ink to write, sometimes it actually is conceptually a far easier notation to understand than Newton's notation. But we'll be bouncing back and forth between these two notations. So one thing that I'll add, thinking about the derivative as a function, this idea of operators. Now with numbers, we've been familiar with operators for quite some time. Add, subtract, multiply, divide. Those are operators put into numbers and you get an output number. There are also operators like the square root. There are operators like, it's hard to write that abstractly, but an exponent, raise something to a power. These are all operators, and we use these on numbers. Now, of course, we can use these operators also on functions. We can add functions, subtract functions, take square roots of functions, exponentiate functions, that sort of thing. So all the numerical operators are also function operators. But it turns out there are some unique function operators that don't work on numbers. And the first one we've learned about is the composition operator, f composed with g, which means that what we're going to do is plug g into f of x. Composition is an operator among functions that is not a numerical operator. And in this video, what we've learned is that the derivative itself acts as an operator. This is an operator whose input is one function and whose output is another function. And so, just as the first derivative is a function, we can think of the first derivative operator as something that sends one function to another function.